Hi, our team consists of Anthony Flores, Sam Duke, and Eric Mason, and we decided to do an engineering economic analysis of Dippin' Dots. Dippin' Dots is renowned because it was the first food technology to use cryogenic freezing, which basically uses liquid nitrogen to lower the temperature to negative 320 degrees Celsius. The person who invented it was this microbiologist named Kurt Jones, and he actually used it originally on bacteria, but then decided to bring it to food because who wouldn't want to bring it to food? The technology uses flash freezing, which basically means that as the liquid mixture enters the freezer, it's frozen in a matter of seconds into these tiny droplets. In November 2011, Dippin' Dots faced financial insecurity and faced bankruptcy. Even though the company was faced with over $10 million in debt, it maintained its commitment to creating fun and making memories, the Dippin' Dots motto. We identified the largest financial barrier as the inability for Dippin' Dots to be stored in grocery store freezers because Dippin' Dots need to be stored at a temperature of negative 40 degrees Celsius, and most grocery store freezers operate at 0 degrees Celsius. So the purpose of this analysis is to highlight methods through which Dippin' Dots can increase its yield and productivity in order to afford the subsidization of these freezers so that they can make up for the lost funds.
So before any intensive analysis, we should first look at the process flow diagram of the overall process of making Dippin' Dots. So Dippin' Dots involves a lot of heat exchangers and mixing processes, and we found that the most time-intensive unit operation is in fact the coating mechanism. So the coating mechanism is used to allow the droplets to clump up to the appropriate size and also add flavor to the Dippin' Dots based on which flavor or which type of ice cream is being made. So the coding mechanism currently being used is a CSTR, and so now we're going to use analysis to understand the differences between a plug flow reactor model and a continuous stir tank reactor model, and see which is better for Dippin' Dots process. So a plug flow reactor model, as can be seen here, involves a certain length, as represented by L, a cross-sectional area A certain distance x, followed by a certain distance dx, a volumetric flow rate v dot, and concentrations of A and B leaving. So the way we modeled this was that reactant A, or the droplets entering this coating mechanism, are then turned into a product B, which is the appropriately sized Dippin' Dots with flavoring. So we modeled this using a reaction mechanism for simplification. So now going into some of the math behind the plug flow reactor, we used a basis where Ca1 was 1 molarity and the V dot was also 1 liter per second. And going through this derivation, we found that the yield of the plug flow reactor is an exponential function dependent on K and tau. So K is defined as the process of the Dippin' Dots droplets turning into the appropriately sized clumps, so the rate of formation of these clumps. And tau is the residence time within the plug flow reactor. So now looking at a CSTR, we did a similar analysis for the yield involving plug flow reactor and making sure that the plug flow reactor volume is normalized for the CSTR. So doing a similar analysis, we found that it's also dependent only on K and tau, but it's more of a ratio type of function.
So to visualize the yield's dependence on residence time and the mixing rate constant, we created two plots, one which plots the yield as a function of residence time, and the other which plots the yield as a function of the mixing rate constant.
So we found that a plug flow reactor goes to 100% yield faster in both cases where we varied residence time and the mixing rate constant. So thus we found that the plug flow reactor for a higher yield and thus higher efficiency for the entire process.
We also wanted to consider how Dippin' Dots might expand itself by reaching out to a wider array of customers. So we wanted to consider how using soy milk instead of regular milk to create vegan-based products would differ. So the main difference between soy milk and regular milk has to do with the viscosity of the droplets. So we wanted to really look at the viscosity and see how that was dependent on the residence time, so we could relate those two as a function of each other. And in order to do that, we conducted a dimensional analysis where we defined a function residence time dependent on viscosity, the pressure of the reactor, the temperature, and the density. And then through this analysis, we found that our dimensionless number, pi1, is equal to the residence time times pressure divided by viscosity.
So using the box equation, So the viscosity can be found by using the temperature of the reactor T and the fat content of regular milk versus soy milk. Regular milk is more viscous than soy milk, which makes sense because it does have a higher fat content than soy milk. This thus means that the residence time of regular milk is larger than that of soy milk. Using a plug flow reactor modeled equation that we saw before, we can then project the yields of regular milk droplets versus soy milk droplets for varying values of K, the mixing rate constant. Regular milk will have a larger yield for any given value of K due to its larger residence time. And in order for soy milk-based Dippin' Dots to be produced, changes in the process are in order to allow for a comparable yield. Remembering our previous dimensional analysis, we understand that residence time can be altered by changing the pump pressure accordingly. Thus, as can be seen, when we no longer assume that the pump pressures are equal, and instead the residence times are equal, then the pump pressure for the soy milk-based Dippin' Dots should be about 41.89% of the pressure used for the regular-based Dippin' Dots. This makes sense because if it's less viscous, it should take less energy to pump it through the plug flow reactor. Thus, less energy would actually be used for the overall process, thus actually leading to more marginal returns for this soy milk-based Dippin' Dots.
So in general, we believe that Dippin' Dots is a high-quality option for ice cream, and we think it really is a way that we're innovating the food industry. It's an example of food engineering and chemical engineering at its finest. If this process were to adopt a plug flow reactor and more vegan-friendly options, then we think that the company would have a chance at expanding itself economically, and that would give it the option to subsidize these sub-zero temperature freezers and distribute Dippin' Dots all around the world.
Thank you for listening to our presentation.